Chapter 3 Modeling with First Order Differential Equations. Section 3.1 Linear Models. This section will look at the applications involving mixtures and series circuits. For the mixture problem, the rate of change or the differential equations of the salt with respect to time is the input rate of salt minus the output rate of salt. The first example, a tank contains 200 liters of fluid in which 50 grams of salt is dissolved. Brine containing 1 gram of salt per liter is then pumped into the tank at a rate of 5 liters per minute. The well-mixed solution is pumped out at the same rate. Find the number A of T of grams of salt in the tank at time T. Let's put information together. A tank contains 200 liters of fluid. So the original volume B is 200, in which 50 grams of salt is dissolved. Then A of T is grams of salt in the tank at time T. At the time 0, A at 0 equals 50 grams. Brine containing 1 gram of salt per liter is then pumped into the tank at the rate of 5 liters per minute. So the concentration that comes in is 1 gram of salt per liter, and the flow rate, the input flow rate, would be 5 liters per minute. And it's also pumped out at the same rate. So the concentration that coming out would be the amount of salt at time t divided by the net volume. And the net volume is from originally 200 liters coming in with a flow rate of 5 liters per minute. For t minute, the volume that coming in is 5 times t and pump out with the same rate, so minus 5t. Therefore, the concentration of the output would be A over 200, and the unit would be gram per liter. The flow rate that coming out is the same, which is 5 liters per minute. To form the differential equations, dA dt, or the rate of change of the amount of salt in grams per the time t as the minute, the unit is grams per minute, equals the salt rate in that coming in minus the salt rate that coming out. Or we can use it as a rate in, rate out. The salt rate that coming in would be the product of the concentration, which is 1 gram per liter, multiplied by the rate in, which is 5 liter per minute, subtracted by the rate out, which is the concentration out, which is A divided by 200, multiplied by the rate out, which is 5. As you see, the unit liter and liter cancel, so then the unit of the right-hand side would be the same as the left-hand side, or gram per minute. Rewrite the differential equations to be dA dt equals 5 minus A divided by 40, from reducing 5 and 200 to be 40. With the initial condition A at 0 equals 50 grams. We can see this as a linear equation or the separable equation. Let's use the linear equation. If we treat it as a linear equation, we write it in the standard form, or dA dt plus 1 over 40 A equals 5 with the form of the linear equation, we get the P at t equals 1 over 40 and the F at t as 5. So will give us to find the mu or the integrating factor as e to the integral pt, which is 1 over 40 with respect to t, or e to the power 1 over 40 times t. The solution or the general solution is a equals 1 over mu integral mu times f at t with respect to t plus c. We have mu as e to the 1 over 40 t multiplied by the integral, the mu, which is e to the 1 over 40 t times f, which is 5 with respect to t plus c. The antiderivative will give us e to the power 1 over 40 t divided by 1 over 40 or multiplied by 40 together with the 5 becomes the coefficient 200 plus c. And then multiply by 1 over e to the 1 over 40 t. Therefore, we get a equals 200 plus c over e to the power 1 over 40 t as a general solution. From the initial condition a at 0 equals 50, find c. So 50 equals 200 plus c over e to the power 0, which is 1. Therefore, c is negative 150. So we get the solution, or the amount of the cell at time t, which is a at t equals 200 minus 150 divided by e to the power 1 over 40 t. If we consider the transient term, the second term is a transient term. Since we take the limit as t approaches infinity, this term will approach 0. Therefore, the equilibrium position or the equilibrium point of this situation will give you the A or amount the A, which is the quantity 200 grams.